Hey everyone, and welcome to the Step-by-Step Explainer. Today, we are setting a pretty major goal for ourselves, which is to build a truly rock-solid foundation in basic mathematics. Now, if you've ever felt that numbers can get, just a little bit overwhelming, absolutely do not worry. We are going to break down some of the absolute most fundamental concepts in math into really easy, conversational, and highly relatable ideas. So let's just dive right into this and master the art of comparing numbers together. All right, so here is our roadmap for today's explainer. We'll start with the basics of ratios, then hit the golden rules, followed by equivalent ratios explained. After that, we'll look at proportions and perfect balance, then the unitary method, and finally, bringing it all together. So, starting off with Section 1, Basics of Ratios, the foundation of comparison. Okay, so I want you to imagine a grandfather, and he wants to compare the wealth of his two grandsons, Ram and Sham. But he wants to do it without revealing the exact amount of money they actually have to anyone else. It's kind of like a secret code. Let's say Ram has 100 rupees and Sham has 200 rupees. Now, if they just go out and tell everyone the exact amounts, it feels a bit clunky, right? Maybe a bit too much information. But if they use a ratio, they can simply say their wealth is distributed 1 to 2. By using division, this 1 to 2 ratio brilliantly shows that Sham has exactly double the wealth of Ram. It completely hides the actual currency amount while perfectly communicating the relationship between the two. And honestly, that is the pure magic of a ratio. It's simply comparison by division. Moving right along to Section 2, the golden rules, getting it right. Before we go further, I've got a quick trick question for you to think about. Can we directly compare 30 minutes to 1.5 hours to find a ratio? Like, is mixing minutes and hours mathematically valid at all? Well, the firm answer is a big, resounding no. You absolutely cannot. And this brilliantly illustrates our golden rules. Rule number 1 states that units must be completely identical. Think about it. You wouldn't compare someone's weight in kilograms to someone else's height in centimeters, right? It makes no sense. So comparing 30 minutes directly to 1.5 hours is a complete unit clash. It's just mathematically invalid. The correct way to handle this? You simply convert those 1.5 hours into 90 minutes. Now you have 30 to 90, which is perfectly valid and ready to go. And then we have rule number 2, which is equally critical. Order is absolute. For example, if a class has 20 boys and 40 girls, the ratio of boys to girls is 20 to 40. But if someone asks you for the ratio of girls to boys, you have to flip it. It becomes 40 to 20. The order of the words strictly, literally dictates the order of the numbers. No exceptions. Next up is Section 3, Equivalent Ratios Explained, Scaling Up. So equivalent ratios work exactly like connected gears in a machine. Let's say we start with a base gear, or base ratio, of 2 to 3. Now that ratio can easily scale up to 4 to 6 by simply multiplying both numbers by 2. If you decide to multiply that original base by 10, it scales all the way up to 20 to 30. Multiply it by 12, and it becomes 24 to 36. Now, on the surface, these ratios look totally different from one another, right? But deep down, when they're simplified, they represent exactly the same value. To move back and forth between your base ratio and the larger, real-world values, you just need to multiply or divide both sides by the exact same unique number. Let's just quickly summarize this multiplier effect step by step so it really sticks. First, you always start with the base ratio. Then you pick a single uniform multiplier. You then take that multiplier and multiply both parts of the ratio, the numerator and the denominator, by that exact same number. The big takeaway here, the so what of this whole concept, is that whether you were comparing 20 apples to 30 oranges or 24 apples to 36 oranges, the foundational relationship remains completely and utterly unchanged at 2 to 3. It's the same core relationship, just scaled differently. That brings us to Section 4, Proportions, Perfect Balance. So what exactly is a proportion? By definition, a proportion is a mathematical statement proving that two distinct ratios are completely equal in their simplified form. We're leveling up here. Instead of just comparing quantities, we are now comparing the ratios themselves to see if they represent a state of perfect balance between two totally different scenarios. You can think of a proportion almost exactly like a perfectly balanced physical scale. Let's look at one side of the scale. Over there, we have the ratio 12 to 18. On the other side of the scale, we have 20 to 30. Now, just looking at them, they certainly don't look the same, do they? But if you take that 12 to 18 and simplify it by dividing both numbers by 6, you get 2 to 3. And if you simplify the 20 to 30 side by dividing both by 10, you also get 2 to 3. Because both sides simplify all the way down to the exact same base ratio, that scale is perfectly balanced. Therefore, we can officially declare that these four quantities are in proportion. Now, simplifying is great, but there is actually an ultimate shortcut test to prove if four numbers are in proportion without having to simplify them down every single time. It's called the golden rule of balance. When you write a proportion out as a sentence, like A is to B as C is to D, the outside numbers, which are A and D, are called the extremes. The inside numbers right in the middle, B and C, are called the means. The math here is just beautifully simple. A proportion is only true if the product of the extremes exactly equals the product of the means. In plain English, that means if you multiply the two outside numbers together, that result must equal the result of the two inside numbers multiplied together. If those two products match perfectly, congratulations, you have a true proportion. Okay, let's just do a quick diagnostic recap before we move into the home stretch. A ratio is all about comparing two quantities of the exact same kind using division. It's finding out how many times larger one thing is than the other, and we use a single colon to show it. A proportion, on the other hand, is all about equality. It equates two different ratios to show they are identical under the surface, usually using a double colon or an equal sign. It fundamentally proves that the scaling happening in one scenario perfectly matches the scaling happening in another. Section 5. The Unitary Method. The Real-World Fix. Now, the unitary method is where this all gets super practical. It's essentially a really simple two-step recipe for real-world problem solving. Step 1. You find the value of one single unit, the unit in unitary, and you do this using division. Step 2. Once you finally know the exact value of that single isolated unit, you can find the value of absolutely any required target amount using multiplication. It really is just first find the cost of one, then multiply to find the cost for many. It is incredibly straightforward, but so powerful. And finally, Section 6, bringing it all together, the synthesis. Let's walk through this really excellent, practical example of a car needing fuel. We are going to use everything we just learned. In Phase 1, you establish a baseline. You notice that your car uses 2 liters of fuel to go 40 kilometers. Boom, that gives us our baseline ratio, 2 to 40. Now, moving to Phase 2, you are planning a much longer road trip of 100 kilometers. So you set up a proportion to ensure the math stays perfectly balanced. You write it out, 2 is to 40 as x is to 100. We don't know x yet. Finally, in Phase 3, you execute the calculation using the unitary method. First, you step down and figure out the fuel needed for just one single kilometer. You divide 2 by 40, which gives you 0.05 liters. Now that you have that golden value of one single unit, you step up. You take that 0.05 and multiply it by your target of 100 kilometers, and you get exactly 5 liters. Ratio, proportion, and the unitary method all working perfectly together to solve a real problem. All right, I want to leave you with a final thought and a bit of a challenge to see if you can apply the step-by-step methods we've learned today. Here's the scenario. If 5 identical pens cost 50 rupees, what exactly is the cost of 8 pens? Use the unitary method we literally just discussed. Remember the steps. First, find the value of just one pen, and then multiply that out, find the value of 8. Run the numbers, trust the process, and leave your calculated answer down in the comments below. Thank you so much for joining me on this explainer, and keep exploring the incredible math that is all around you.